Okay, in our final video here, I just want to give you a little bit to go on in terms of hash functions. I've shown you one, but let me just give you some qualities of common good hash functions. So properties of a good hash function is that it should lead to the smallest number of collisions as possible, and it shouldn't be too much work to compute. So, we require it for every lookup, insertion, deletion, so we call these hash functions very often. So let's start by just thinking about what's the worst case for a hash function. And for worst case, just focus on this one. What would give you a maximum number of collisions? Well, if your hash function just returned the exact same value every time, that's obviously going to maximize collisions. So that's sort of your worst case scenario. Well, you can also end up with bad hash functions sort of inadvertently. So let's say that your keys are 10-digit phone numbers. Your universe is 10 to the 10, but let's say we only want to store 1,000 items. So our items are going to look something like this. A terrible hash function might be to take the first 3 digits of your numbers. The 3 digits will give us our 1,000 slots. And what do you notice about these numbers? They would all sort of map to the exact same spot. So that would be a terrible hash function that seemed reasonable to begin with. What about a hash function that takes the last 3 digits? So this would do better in this example, but it still sort of favors some buckets instead of others. Why might that be? Well, if you have ever watched sort of any infomercials, you always end up with those 1-800 numbers that, like, I don't know, Cash Clark, I don't know. They're words. Advertisers try to be pretty clever to make their phone numbers memorable. So when you type in a phone number, a lot of times the last 3 digits are things that are commonly the last 3 letters of words, so word endings. So not great, not terrible. So you'd still probably want to perform some sort of operation on even phone numbers, even though they are numbers themselves. So in general, you have objects. You want to produce integers from those objects and then do some sort of compression. So that would be like taking the number you get mod n. So if we take strings for an example, a crude hash function might be to create a unique number from the characters, and then this would be similar to DGB2. Your compression would just be to take that integer mod n. But something we've sort of skirted a couple times is how do you actually choose n? Well, it turns out there are some better values for n than others. Namely, if you choose n to be a prime number, that will reduce the chances of collisions just based off the way that wrapping around using that modulus operation works. That's something we'll talk about with universal hashing in the next set of slides. And for similar reasons, a good couple of rules of thumb is to not choose something too near a power of 2 and to choose something that's not too near a power of 10. Alright, so what's your hash table summary? You make a big array. You create some function that converts elements into integers. That's called hashing. You store elements in the array at the index specified by the function created in the previous step. Do something interesting if 2 elements collide. So, open addressing or separate chaining. And then you rehash when your hash table gets too large. So what does it mean to resize? If your entries array has a space for, let's say, 7 elements, maybe you double that to 14. That's no longer a prime number, so maybe you round this thing up to 17. When do you usually resize the hash table? A good rule of thumb is when you hit 75%. That's mostly from sort of empirical results. People, ran a bunch of hash functions in real world scenarios. 75% gives you a pretty good measurable performance. And unlike arrays, which usually double in size, it turns out the way that people mostly use hash functions, it makes sense to just increase the size by 1.5 times. So, my example up here is not perfect.